So, Sam, you're connecting from UK. I just want to tell a few words before you go on with your presentation. So, Sam Newman, he's a technologist, he's an independent consultant, speaker, and author of Building Microservices and Monolith Microservices. He specializes in helping people to ship software fast. He worked extensively with the cloud, continuous delivery, and microservices, and he is especially preoccupied with understanding how to more easily deploy working software into production. So the name of the talk, Hiding the Lead, and Sam Newman, Microsoft MVP. I think, Sam, you can say a few words about yourself when you begin. And after you finish, I'll be back with the questions.
Thank you so much. I'm not an MVP yet, but you know. Anyway,
Microsoft MVP. It says in the bio, so someone lied.
Well, unless I've been promoted somehow without anyone telling me about it, I think I get a trophy or some kind of special jacket if they make me an MVP. Okay. I think they just send you like a bronze full-size statue of yourself. At least that's what I assume all the MVPs have in their back gardens.
Okay, so let's say a future MVP of Microsoft. Why not? That's possible. Still, yeah.
Thank you so much.
Okay, so Sam, take it away with your presentation, and we'll be back in the questions. I'm looking now to the chat, guys. So your questions in the chat. Take it away, Sam.
Thank you so much. Thanks everyone for coming along today. I hope wherever you are, you're wrapped up warm and have a nice cup of coffee. I have not started today with red wine and honey because even I have to draw the line somewhere. We're going to be talking today about the importance of hiding stuff when it comes to microservices. One of the issues with microservices is that we want these things to be independently changeable, independently deployable, but we often get into issues where we find that they're overly tangled together. And that's what I want to talk to you about today. As was mentioned, I have previously written a book called Building Microservices. I'm working on a second edition of that book, which will be out the middle of next year. An early access version of the second edition of Building Microservices is available. You can find more information about that over at my website. And my most recent book, Monolith to Microservices, was released at the end of last year. This is a book about how you take an existing monolithic application or perhaps some service that's got too big and how you break that apart to kind of create a microservice architecture. So microservices are interesting, they're cool, everyone likes them, we think. Actually, they're incredibly dangerous things, and you really should not do them unless you've really thought it through and tried everything else first. But that said, if you have decided to adopt microservices, probably the most important rule to remember is the property we want from our microservice architecture is that of independent deployability. I should be able to go to a microservice, in this case, the accounts microservice, make a change to that microservice and deploy it into a production environment and then release that functionality to my external users without having to touch or change any other part of the system. And it's from this property of independent deployability that so many of the benefits that people look to from a microservice architecture come from. Now, to make independent deployability work, though, we do have to think very carefully about the effects that might have on the wider system. In this example here, when I make a change to that account service and roll out that new version of it, how do I make sure that I haven't broken an upstream consumer, in this case, the upstream customer service? In fact, I need to avoid this situation, don't I? Because I need to have independent deployability. I need to have confidence that this is going to work properly. When I make a change, and then deploy that change, I really want to be pretty sure that I'm not going to cause some awful ripple effect across the rest of my system. And in fact, that's vital. If you don't have that certainty, you're not going to be able to change things independently. So to get that certainty, we need to make sure that we haven't broken the compatibility with our upstream consumers. Essentially, independent deployability requires a degree of stability around an interface. What that means is whatever service interfaces you expose, you need to get very good at maintaining backwards compatibility. And if you can't maintain backwards compatibility, then you start getting problems like this, and that's an issue. Now, if we go back into the mists of time, we used to build most software. Well, the software was built on mainframes. And over time, this is back in the days when we had a very small number of very large machines. And these machines got more and more powerful. And so the programs we wrote to run on these mainframes also grew and grew and grew. And people realized, well, these programs are becoming difficult to maintain. They are becoming too big. So what do? Well, we break those big programs down into smaller pieces. And talks to really the rise of modular software and structured programming. So rather than having just one big blob of a program that we dropped onto a mainframe, instead our software would consist of multiple modules that connect together to create the application. The idea is that these modules allow for a degree of independent working. I could have people working on module A and some other people working on module C, and they could do some work in parallel. Because by breaking our work apart into modules, by breaking our software apart into modules, we allow for those modules to be worked on independently without requiring too much coordination. In fact, if you had one team working on module A and another team in this example here working on module C, the only thing that they should have to coordinate around is about the interface between module A and module C. If I make a change inside module C that doesn't change that interface, we should be able to work in parallel. And this became a way to not only allow larger teams to build software in a more efficient way, it also gave you kind of some more obvious structure of your software and your programs as well. Modules are also useful here in terms of reuse. Some of these modules could have come from other programs or or maybe either in-house modules or external modules. So this is all fine. This is kind of pretty standard ideas, right? Modular software, right? It's not a new idea. The problem is that our concepts of modules now are a little bit more murky, and most of our modern runtimes don't actually handle modules very well. A big part about modules is hiding information. We'll come to that in a minute. And typically the way we limit our hiding of information in, say, languages like C# or Java, we kind of think about things like packages and namespaces that allow us to hide symbols. And then we have visibility on keywords. And the idea being is that we can sort of say, well, this boundary between these two things and everything underneath that boundary is something that you cannot see. We even go further now, of course. We maybe take those bundles of code and we package them together in NPMs, gem files, jar files, NuGet packages to allow for reuse in form of things like open source code. I suspect most of you are putting in a number of open source libraries. To an extent, you're kind of making use of this property of software that you can build it from modules. So this idea of modular software helped us grow our systems into more complex systems that didn't become completely unmaintainable. At least that's the hope. Now, the nice thing about modules and modular software is it starts to look a lot like microservices. If we think about a microservice architecture, what we basically have is collections of functionality that have clear interfaces between them. We want to be able to work on those different collections of functionality in an independent fashion. The difference maybe between microservices and earlier modular software is that the modules are now separate processes that run on different computers. This gives us the ability to do things like independent scaling. The communication between modules is now not in the form of, say, a method call within a single piece of infrastructure. It's now being done via network calls. And unlike some other modular software, we've got the ability to deploy these new versions of these modules independently. Now, it's kind of worth dwelling on that for a moment. I don't really have the ability to hotspot modules on the JVM or on the CLR. And, things like OSGI really don't cut it when you look into the detail of it. We do, of course, have this capability on something like the Beam VM. And guess what? An awful lot of mainframes did allow for independent deployability of what we've lost. But fundamentally, we can view microservices as a form of modular architecture. The reason we look at them differently now, of course, is because the economies of computing have changed. We've gone from having a small number of very large machines to now having a large number of, relatively speaking, smaller machines, although I would hazard a guess that each one of these servers here probably has the same kind of characteristics as some mainframes in terms of computing power, such as the effect of things like Moore's law. Now, in terms of creating modular software and finding what makes a good modular boundary, this is useful for us in the world of microservices. If microservices are a form of modular architecture, then it follows that we can use a lot of the ideas from modular architecture in our thinking about defining microservice boundaries. And I mentioned this in passing almost in my first book, but it's a concept which subsequently I've come to realize is almost one of the most important concepts when it comes to creating a microservice architecture. And that's this idea of something called information hiding. As a concept, this was first explored by David Parnas in his paper on the criteria to be used in decomposing systems into modules back in 1971. And so Parnas was looking at the kind of different techniques by which we can define a boundary around a module, the interface between modules. He was looking to make it easier for people to work independently, for teams to work independently. And the technique he alighted on is what he then went on to call information hiding. The idea that you should hide as much information as possible inside the module boundary. Anything that you expose out of your module boundary becomes part of the contract between your module and core. And that contract then needs to be something that you have to maintain going forwards if you want to allow for these things to change independently from one another. Adrian Collier a few years ago did a really nice series of blog posts looking back at some of the Parnas papers, and he went through the papers, he sort of crossed out the word module, put in the word microservices, and then read the whole papers back again and said, you know what? This all stacks up. All of the things that Parnas seems to be saying about modules seem to apply really well for microservices. So these are really worth reading over because, I mean, Adrian's very insightful anyway, but these are kind of a nice summation of these papers if you don't want to go into the having to read the originals from the 70s. In fact, it's in quite a nice moment, David Parnas actually comments back on the blog posts, which is quite a nice touch. So when we think about information hiding, the idea here is we hide our secrets. We want to hide information from the outside world. Anything we hide, we can change safely. Anything we expose becomes part of our public contract that we have to maintain. Consider a microservice like here. We've got the accounts microservice, and I've got all this functionality that sits inside my service boundary. These could be functions, methods, or whatever else. I have an external service here, the shipping microservice, and it reaches into my internal implementation. It reaches into my database. The problem at this point is if you can reach into somebody else's internal implementation, reach into their data store, I could make a change to part of this implementation, and it now breaks that external contract with the outside world. And this is just the problem, how it can manifest itself is as a developer, you go to work on the account service and you're now uncertain as to what things can be changed safely. Can I refactor that? Could I remove that column? Could I add a constraint on that database table? Could I refactor this class? And suddenly doing what feel like quite innocent changes end up causing unforeseen breakages elsewhere in your system. Information hiding is as much about giving clarity to the developer working on this given microservice as it is about being explicit to consumers as to what it is you provide. So with information hiding, we want to clearly differentiate between the things that are hidden and the things that are shared. So we would say, look, all of this stuff here, all of this code, all of this data storage, that is yours. That is under your control. Nobody else from the outside world can ever see this information. Hide your secrets. Then be very explicit about what is hidden and what is shared. Anything in the shared world, which is part of your service interface, and you can, of course, expose multiple service interfaces if you want, this stuff is what you have to be very careful about. As a developer, if I change anything in that shared world, there's a danger that I might end up breaking an external consumer. Therefore, I know I'm going to be super careful to maintain compatibility. On the other hand, anything inside the hidden world, I can do whatever I want. And then obviously I have to maintain the mapping between those two, but that becomes an internal service concern. So being explicit about being shared and being hidden is really, really important to maintain and make it easy to maintain backwards compatibility. This also, of course, is useful from the point of view of the shipping microservice in this example here, because they have a clear understanding about what they can expect. Now, we of course do have a whole host of things where we accidentally break compatibility. Here's a classic example. It's a piece, little snippet of Java code. And I've got some particular customer class. And quite a common thing, especially if you're doing something like, say, JSON serialization over your network interfaces, would be to take a class like this, take an instance of an object like this, and basically just serialize the fields. So you walk all the fields of this class, and you convert them into, say, a JSON payload. So here I've got an ID, a name, and an age field. And, a developer might look at this piece of code and they think, oh, hang on, I've got the age of a person here. It doesn't really make a lot of sense for us to store the age of a person, does it? Because, well, the age could change. Like if we clocked over into the next day, that could be their birthday and their age could have updated. So rather than storing that as a field inside our code, it would make more sense for us to actually store the date of birth in the code, and then we could generate the age from that. So instead, I decide to come up with like this. So I say, okay, I've got the ID name and now I've got the date of birth. But oh no, when I generate that payload, I discover, oh, that box is in the wrong place. But I discover now I'm not exporting an age, I'm actually now exposing a date of birth instead. And suddenly I've broken compatibility. And so if you're going to do a mapping like this from a data structure to a JSON payload like this, and you're doing that kind of in an automated fashion, in this context here, in this example here, what clue is there to a developer refactoring that piece of code that this actually changes the public contract? None. So there's a couple of options here. One is to actually use annotations. So I could use some kind of annotation-based introspection to put like field names on these things. So I could put an attribute on those fields to say this is going to be exposed. And then at least when I'm looking at it, I know, hang on, if I change that, I'm potentially breaking the external contract. Another way we could do this is actually to not automatically map from an internal representation to an external one and do it explicitly instead. And this is where you might use something like a data transfer object. So here I have my internal representation, and then I create a DTO, a data transfer object, that is going to be what I then serialize. So in the creation of this DTO, I would take that date of birth field, generate the age as part of that, and put that in the DTO. I would then serialize that data transfer object. Now, this for me as a developer becomes a bit clearer to me. So if I make a change to the customer, I'm going to have to update the DTO, because probably the DTO creation would at that point would not compile, for example, on a statically typed language. And so then it becomes a lot more, okay, well, now I've got to redo the mapping. So DTOs can actually help you reduce kind of the impact in terms of compatibility with external parties. There are other things that we can do though, because DTOs might be it might be too much work for a lot of people, or it might feel like a lot of, I'm just having to redo the same things over and over again. Now, I want to say here that if DTOs are one way to help you maintain backwards compatibility, I think it's a good thing to do, even if it takes you a bit longer, because guess what? Changing your external contract should be hard. You don't want to make that easy. You want to make that a very conscious decision. So if DTOs help you make that separation between internal and external very explicit, then they may be worth it to you. Another way, though, that we can be explicit about what is shared and what is hidden is to have an explicit contract, right? In this situation here, module B is talking to module D. What we want to know is have an explicit understanding of what it is that our consumers expect. That then helps us understand what can change and what can't. Another way we can be explicit is schemas. I'm a big fan of having an explicit schema for my service interface. I love schemas for this purpose. Now, whether or not you have an explicit schema or not, you do have a schema. Many people, in fact, most people I speak to who use JSON over HTTP say we don't use schemas. And I counter that by saying, well, you do. Because when a consumer reads your JSON payload, they have expectations as to the structure of that JSON payload. They expect certain names to be in certain places. They expect the names to have certain types of values. When I read this field, I expect it to be an integer. When I read that field, I expect it to be another JSON object. It's just the problem is when you don't have an explicit schema, though that understanding is entirely implicit. And so now it becomes unclear to you as to what changes I can make. I would argue that an explicit contract, an explicit schema for a service interface is analogous to static typing, right? An explicit schema can help us validate our compatibility, or at least a large amount of our issues around compatibility quite easily. If you're using something like JSON, for example, you can make use of JSON schema, and you can define a schema that you can then validate and actually even do comparisons around backwards compatibility. You might be using protocol buffers, an explicit schema with tooling around it to check compatibility. Protolog is a great example of this. This is a command line tool that can actually compare two different versions of two different protobuffer files and will fail if they're not backwards compatible. Guess what? That type of tool is the thing you put in your build. If you're a developer, you've made a change to the protocol specification, you think you've made a change to that protocol specification which is backwards compatible, this tool could pick it up and say, yes, you have, or no, you haven't. You could fail the build before you even get to production. And how great is that? Immediately, I've got a whole load of my potentially backwards incompatible changes. We've got similar things out there as well for the Open API specification. So Open API diff, there's about 4 tools I've found called Open API diff. This is the one actually from the Open API sort of people themselves. But this is something you can embed in your build process. So when you make a change to that REST endpoint, If it's backwards incompatible, you can have it fail the build. The Kafka schema registry, which you don't have to use for Kafka communication, you just need Kafka to run it, but you could easily use this for other kinds of communication. When you upload a schema into the registry, you can actually configure it to say, no, actually, that's a backwards incompatible change. And the nice thing about the schema registry is it supports protobufs, and it supports Avro, and it supports JSON. So that's really handy. Now, of course, in terms of compatibility checking, schemas will only really help you look at the structure of your service interfaces. You probably also will want to validate that you haven't broken the semantics, the behavior of your endpoint. So testing is, of course, also useful. So that's information hiding, thinking about how we can get better about hiding information. So let's look at some other ideas from modular programming and think about how they apply within our microservice architecture. And here we start looking into some of the stuff that came out of the world of structured programming. We have the two big terms in this world that we could talk about today are the concepts of coupling and cohesion. And these are terms that we often use without being explicit about what they mean. But I'm going to try and be at least a little bit more explicit in the context of a microservice architecture. There's lots of stuff out there about what these terms mean in terms of code. I think they have slightly different meanings in terms of systems architectures, but let's take a look. Normally, when we talk about coupling, we talk about the idea that we want a low degree of coupling. And we'll talk about what that means in a minute. But we also want a strong degree of cohesion, strong or high cohesion. Now, cohesion is the property of a system where the code that changes together stays together. If I've got some functionality related to invoicing, I don't want to have to go and change that in like 15 different places in my code base or across my services architecture. That slows down my pace of change. It increases the chance that actually I'm going to miss one of those places and now I've got a bug or an inconsistent set of behavior. When we see low cohesion in a services architecture, what we often see is this idea that functionality is often spread across lots of layers of our systems. Fundamentally, most layered architectures out there are architectural examples of weak cohesion of business functionality. This is why I think stuff like bimodal IT and paste-layered architecture is kind of a bad idea, right? I mean, bimodal IT says you've got two speeds of IT, and it's like, yes, if you adopt bimodal IT, you've got two speeds, slow and slower. When you have layered systems like this, you often have weak cohesion. You'll find yourself needing to coordinate changes in multiple different places. And this is what we try and do with microservices is rather than slicing kind of horizontally, we try and slice vertically to reduce this problem. Now, coupling is a degree to which changing one thing requires a change in another. And these properties of coupling and cohesion are related. If my functionality is spread all over the place, I have low cohesion. When I need to update that functionality, I'm going to have to update all those bits at the same time. So these concepts of coupling and cohesion are related. And we want loose coupling with our microservices because we want to be able to change those microservices independently from one another. This interrelationship between coupling and cohesion is referred to as Constantine's law. It's not actually something that Larry Constantine came up with, this law, but it was it's sort of a law just named after him because of the work that he had done. And the Constantine's law states that a structure is stable if the cohesion is strong and the coupling is low. So a structure is stable. So what we're talking about here is the interface. And we want a stable interface for our microservices because that gives that stability, makes it easier for us to do independent deployability. So we want stability. And what we're learning here is that we want cohesion to be strong. So we want all the functionality that's related to kind of be in the same space. And that will also in turn probably help us reduce our coupling. So actually, if you improve your situation in regards to cohesion, you will likely also improve your situation in regards to coupling. Put that around the other way, if your cohesion gets worse, your coupling will also become worse as well. And that's quite useful to us because we can understand that we can improve our systems architecture by addressing either of those issues. Mike Nygaard's got a nice quote. He says that, now of course the problem is we get choices about how we organize our code. And you think about a traditional layered architecture, your presentation, business and data access layer, choices have been made about how we break that architecture apart. I would maintain that that is an example architecture where we have low cohesion of business functionality. Mike Nygaard says that cohesion is coupling we like, right? Because we group code together that's going to change together, but we accept that once it's all in one box, it's sort of coupled together. So we kind of have to understand, well, is it all right for all that stuff to be in one place? Microservices said, Well, yeah, if it's all the functionality related to invoicing or order placement or, a recommendation, then sure, all the functionality around how we handle recommendations is in one place. And that kind of makes logical sense to me. Now, within a microservice architecture, we want low coupling, but coupling comes in different forms. So I'm going to take you through a few different types of coupling, at least in terms of independent change here, and talk about how they manifest themselves in a microservice architecture and what we can do about them. So we're going to talk about domain coupling, pass-through coupling, common coupling, and content coupling. Now, what we're going to write that these forms of coupling become worse. We're going to start off with an easy one, which is domain coupling. And domain coupling really is the property by which one microservice is coupled to the domain of another microservice. And inherently, some degree of domain coupling is sort of unavoidable. Microservices exist to be called and to call other things. In this example here, I have an order processor. That order processor is reserving stock on the warehouse. It's taking payment from the payment service. And it has to have that relationship because stock management is done by the warehouse, not by the order processor. So I have to go to the warehouse and ask it to reserve stock. Payments are also handled by the payment microservice. I don't do payments myself. So I have to go to the payments microservice and say, take payment. And that's kind of, to an extent, is unavoidable. When you move into a microservice architecture, you're accepting some degree of domain coupling is essential. Now, of course, here there is no domain coupling between the warehouse and the payment service. They don't know about each other. They don't need to communicate with each other. A change to the warehouse is never going to impact the payment service because there's no connection between them. So we can still look to reduce domain coupling by avoiding things having to talk to each other. The order processor in this situation, if I change the domain behavior of, say, the warehouse or the payment service, that could have an effect on the order processor. Now, whenever you see a microservice that has lots of outbound connections that's talking to loads of services, and anything called a processor is often a sign that might be what's happening. That can be a sign that it's doing a lot of stuff. It's maybe centralized a bunch of logic. This could be an orchestration type unit or something like that. So it's something to watch for. You don't want too many services that talk to too many other services because that kind of form of domain coupling can be a bit harder to work with. So that's domain coupling. To a degree is unavoidable, but we can at least, limit it by ensuring that only the microservices that really need to talk to each other do talk to each other. That limits the impact if we make any changes that might be breaking in the future. Another form of coupling that does come up is what's called pass-through coupling. It's previously sort of known as tramp coupling, but I prefer the term pass-through coupling. The way pass-through coupling works is we're in a situation here, I've got an order processor talking to a warehouse, and I'm sending the warehouse this send order request. So I'm saying, here are all the items, and here's a shipping manifest. Now, it turns out the warehouse only cares about the items that are being sent. That shipping manifest that we pass through, it kind of just passes on to the shipping microservice. So the shipping microservice needs a shipping manifest. The order processor provides that, and the warehouse here is just sort of proxying that data through. So this is kind of an increased form of coupling. Now, depending on how we've implemented that shipping manifest, a change in the shipping manifest might require not only that the order processor changes because the shipping manifest structure is different, but we might also have to change the warehouse service. If you're doing pass-through coupling like this, what you'd ideally like, if the warehouse is really just proxying that data, you wouldn't want it to try and unpack it. So sort of treat that sort of thing as a blob, and your life will be better off. There are other things that we could do, though, to change this form of coupling. One option would be to, rather than sort of passing the shipping manifest to the warehouse and then having it pass on, is that we could do it ourselves. So the order processor already has to create the shipping manifest. So why don't we do something like this? We go to the warehouse and we say, okay, here's the order. Then we go to the shipping microservice and say, here's the shipping manifest. So this is shifting from pass-through coupling to kind of domain coupling. Now, in this particular situation, I'm not sure if I'd like this model as much. This pushes us much more towards an orchestrated model. So if my order processor was already doing a lot of work, I might not want to do this. I might want to leave that kind of handling of the shipping manifest in the world of the warehouse. Another way to handle this would be to hide the concept of a shipping manifest from the order processor in the first place. So instead, what I might do is I might say just create a send order request with the items being sent. I might provide some additional information that's sufficient to be able to create a shipping manifest, but I'm never aware of what a shipping manifest is. I would then pass that send order request to the warehouse microservice. It would then pull out the information it needs and use that to generate a shipping manifest that it then gives to the shipping microservice. So the nice thing about this is that sort of the shipping manifest in this world, if that changes, it doesn't affect the order processor. And this is what we're always thinking about when we're hiding information. If we hide information and limit access to that information as much as possible, if we change the nature of that information, we limit the impact. So if the only people that know what a shipping manifest is the warehouse microservice or the shipping microservice, then if I change the manifest, I've limited the impact. The order processor in this particular world would be unaffected. Let's take a look at common coupling now. And common coupling is a situation where multiple microservices are coupled to the same commonly externally defined data structure. So this could be a database table, a database itself, or it could be something like a cache, so a structured cache. So in this example here, we've got a warehouse which is maintaining a sort of publicly available, and public within the context of our system, is managing stock levels, and it's actually updating, say, a stock level cache. And so we have, fields and stock values and everything else. The order processor is reading from that cache, and the forecasting service here is also reading right from that cache. Now, this kind of data, if we make a change to that structure, that's going to impact multiple services. So with common coupling, the degree of coupling is increased. If we make a change to that structure, we can have a much bigger impact. And this is something you see with those forms of coupling. As the coupling forms become stronger and stronger and stronger, the impact of any breaking change increases as well. Now, in this situation here, if I say had effectively a common in-memory data structure here that all of these microservices were able to access, I would have to be super careful about making any changes. And again, unless I put some explicit schema around what is in this data structure, it might be quite difficult for me to reason about what changes can be safely made. And it's kind of interesting when we think about, actually, if I was just, say, putting proto buffers into, say, a Redis or a memcached instance or something like that, at least I've got the specification of what that data type looks like, and I can make sure that everyone's using the same schema and that any changes are backwards compatible. But if I'm putting that into a database, that's a bit more difficult. Comparing database versions to try and work out what are backwards compatible changes is a non-trivial exercise, because the complexity of a database schema is significantly greater than the complexity of the schemas that we use for inter-process communication. So validating if I make a change to that stock level structure is okay is quite difficult. Now we can take this a bit to a kind of a worse degree if you want. We've got to common coupling, which isn't great. Sometimes it's needed, but you really do your best to try and avoid it. We now go to the worst form of coupling, which is called content coupling, otherwise known as pathological coupling. So here I've got my shipping microservice, and my shipping microservice is reading and writing data from a database table. This is fine, right? And it's a database that is owned by the order microservice, and we sort of treat that microservice like a black box, ideally. Here we have the well-behaved order processor, and that order processor is coming along, and it's asking the order microservice to make some changes to the state of an order. It's can you move this status being placed to paid? Okay, and that's the kind of thing the order processor might do, and it would go make a request of the order microservice. And of course, what the order microservice would do is it would look at its local state and it'd say, okay, you want me to move the state of order 123 from placed to paid. Okay, that's an allowable state transition. So you can look at its data, and based on the logic inside that microservice, the order microservice, we can say, what you've asked me to do is an acceptable state transition. I will let that happen, and that's fine. But along comes the badly behaved warehouse microservice, and somehow it's directly accessing our database. Now, this can be bad when it's reading from our database structure, because now we can't easily change that database structure, but it gets worse if it's actually updating that data as well. In this example here, what if the warehouse microservice is also changing the status of orders? It's saying, I want you to move from status paid to status shipped. But remember here, when the warehouse does that, and if it's talking directly to a database, it's not asking the order microservice to do something. It's doing it directly. I'm going straight into the database and I'm changing your data. So the warehouse in this world is bypassing any logic that's inside the order microservice. So we're bypassing information hiding, but we're also bypassing any logic inside the order microservice that defines what are acceptable state transitions of this piece of data. What happens if the warehouse has a different view of the allowable transitions for order state than the order microservice does? Well, then we get data in inconsistent states. We've also got stuff around how state changes, the same piece of state changes both in the warehouse microservice and in the order microservice. So we've got, duplication of code. And we've also got low cohesion as well, because a low degree of cohesion, because now I've got functionality for updating the same piece of data in the warehouse and in the order. Effectively, at this point, I'm trying to manage a distributed state machine. Okay, I've got different people in different processes all updating the same piece of state. And implementing a normal state machine in a single process is difficult enough, let alone doing that across a distributed system. It now becomes very unclear to me if I'm working on the order microservice as to what I can safely change. How do I work out what expectation of my shipping database? How would I work out what the warehouse even does to my data? Now, hopefully, even if you've allowed something like this, that you've made sure that all of those other microservices have their own accounts on the database, their own set of credentials. So then you could at least see, okay, the warehouse can only see these tables. So that limits it already. That's a bit easier. But what are they doing on those tables? Which columns do they care about? What expectations do they have around any of kind of the restrictions on the database, or kind of like the rules about nullable columns and things like that? How am I going to work out what they do? Well, maybe I'm looking at the database logs, trying to understand what the warehouse does to this table before I know if I can make a change. Or I'm having to look at the code of the warehouse microservice. Once you're in this world, it becomes incredibly difficult to understand what changes can be safely made. Aside from the fact that these systems are going to take you longer to change because you've got code spread around the system, I'm now in a place where I don't no longer feel confident that I can change my service. And if I'm not confident that I can change my microservice, then that's going to massively impact my productivity. Content coupling of this form is also known as pathological coupling for a reason, right? It's bad and we want to avoid it. The way to avoid it in this situation is quite straightforward, really. Have the warehouse be well behaved. Have the warehouse go and ask the order processor to make state transitions, and then have it you make use of the logic inside the order microservice. That way we never talk directly to the database. The only information we see about an order is via that service interface, and we have a well-defined understanding about what we can change and what we can't. So when we think about those types of coupling, we kind of, we go from least worst to worst, right? Content coupling is the worst. And so when you encounter different forms of coupling, what you're trying to do is push it more to the left. The looser the degree of coupling that you have, the more you'll find you'll increase the cohesion of your software. The easier it will be for you to maintain backwards compatibility of your interfaces. And the easier you're going to find it to get the benefit out of microservices. The more you suffer from coupling to the right of this spectrum, if you've got large amounts of content coupling going on in your system, you'll find your architecture becomes a giant tangled mess. Worst of all, it might become what we call the distributed monolith. A monolith being a unit of deployment, a distributed monolith being a distributed system that you can only deploy as a single monolithic system, which is a bit of a pain to deal with because you've got all the complexity then of a distributed system, and a distributed monolith can be just as complicated to deal with as a microservice architecture, but you don't get any of the benefits because you still have to deal with the thing as a big giant unit. So you have a massively much more complicated deployment process. So if you do encounter different forms of coupling, try and push it to the left. Now, we've got plenty of time for questions, which is great, but just before I get there, let's summarize. Information hiding is really, really important. When you're creating a microservice, be really explicit about what can change and what can't. Make any and all of your service interfaces that your microservices expose very explicit. Consider the use of explicit schemas. I really do think they're a great idea. And for modern serialization protocols, the schema definitions are pretty good now, and the tooling around them is pretty good as well. And these things can help you pick up potentially breaking changes before you ever deploy your software. If you have an explicit schema, you have that possibility. You should also potentially look at things like consumer-driven contract testing, things like PACT as well. But for me, this is where you're thinking about an explicit schema as being analogous to static typing. With a statically typed language, my compiler picks up a bunch of problems. I then can limit what I have to pick up with tests to just the behavior of my system. The same thing happens with microservices. An explicit interface and explicit schema allows schema validation and backwards compatibility checking to pick up a whole bunch of issues. Then you limit your testing to only having to pick up the the behavioral changes in your software. Some coupling is worse than others, right? Some degree of coupling is to an extent unavoidable because microservices do exist to be called. So you should expect some degree of domain coupling. But what if you encounter it, just try and push that stuff to the left. Try and reduce the forms of coupling. Don't share databases, right? As in, don't reach into somebody else's database. That way lies madness, right? Even common coupling, where you might have a shared database that everyone reads and writes from, is really difficult and really problematic. Try and avoid those cases where you have shared data stores. Things like caches, for example, consider whether or not you actually want a schema about the data you're putting into that cache. And you can use proto buffers and things like that or for cache regions if you want to. Information, low coupling, strong cohesion, all of these things lead us to being able to achieve this property of independent deployability. And that's what we're aiming for. And if there's only one thing you remember about information hiding. Hide as much information as possible. Only expose things if someone needs it. Think outside in. What do people need? And I'll give them the bare minimum of what they need. Don't think inside out. What could I possibly share? Hide as little as possible. You can always expose information later on that you'd previously hidden. But the more you hide, the easier it's going to be for you to maintain backwards compatibility. Once you've exposed something over your service interface, it's quite hard to put the genie back in the bottle if you then want to change that structure. But above all, make it as explicit as possible, both to yourself who's working on that microservice as to what you can change freely, but also to the consumer of your microservice as to what they can expect from you. And for this reason, I do think that having an explicit schema is really underrated. Now, there's loads more information about my new book. Monitor Microservices is up there, links to how you can read that book. There's also links on my website to how you can get access to the early access edition of Building Microservices. That Building Microservices second edition will be out in the middle of next year. So what you'll be able to read now is fairly rough and ready, but basically it's available to you on the Aurelia platform. More links about that and the other information about the work that I do for companies all over the world is also available on that website as well. I do training, advisory work for startups. I do, consulting and all that kind of jazz. But with that in mind, I think we are done. And we have time, I'm hoping, for questions.
Yes. Thank you, Sam. We have time for questions, and we have quite a few questions. So let's begin. Ernestus is asking, modular structure is something everyone seeks for at least. However, having agile ways of working, it is hard to do a proper upfront work to get with proper boundaries. So rework might be inevitable. Any insights in this area? Does high cohesive modular monolith most of the time is a consequence of rework rather than initial solution, since we don't have enough time for upfront in agile?
So firstly, Agile does not say that you shouldn't do any upfront thinking. Agile doesn't say that you shouldn't think about your system design. Agile says none of those things. If you choose to implement an Agile process where you do no thinking about your system architecture or design and just start churning out code, then don't be surprised when you get a big ball of mud. When you look into actually how the concept of Agile and systems architecture, what we're saying is we want to do just enough. The problem with IT is the pendulum always goes from one extreme to the other. We saw situations in the past where people would spend 6 months to a year designing a system and then they start actually building it. And that, of course, is crazy. But guess what? You can take a few days to think about your system design, do a bit of development, realize how the design is going, and then tweak that. Your architecture should be a constant thing you're thinking about and evolving. And there is nothing in Agile that says that you can't do that. It's up to you to decide how much of that upfront work you want to do. And honestly, we're not talking about months here. We're talking about a few days here and there. And it should be, but your thought about your system design and your architecture should be a constant concern throughout your software development process.
Thank you, Sam. More questions, and they are piling up, so that's great. Almontas is asking, what are your thoughts on versioning service resources? For example, service has 3 versions, but all versions have the exact same response request models. Would you share the model across versions or split them into folders? Version 1, version 2, version 3, etc.
I mean, so how you come up with the version number is kind of not that super important. I think the idea, though, of a single microservice exposing multiple service versions can make a lot of sense, especially in situations where you do make backwards incompatible changes. So most of what I talked about today was about reducing the chance of you making a breaking change. But every now and then we do need to make a breaking change. When we do that, we still want independent deployability, though. So it follows, though, if I want to make a breaking change to an API version, for example, and I don't want to force my consumer to upgrade at the same minute that I deploy my new microservice version, then I'm going to have to support both the old and the new endpoints at the same time. So having a microservice that can expose multiple versions potentially of its endpoints makes sense, because you then allow consumers time to migrate. In terms of exactly how you implement that is going to depend a little bit on your communication technology. I've spoken to big REST people that, are REST purists, and I'll get different reactions about whether or not you should have like a /v1 or /v2 in your URI path, or you should do it in an accept header. One of the issues around that, putting it in the URI path, is only maybe parts of your API might be backwards incompatible. Now, if I just add on new functionality that is backwards compatible, I don't really feel the need in most situations to rev a version number, because things that could talk to version 1 before can still talk to version 1 now. I think a lot of people overcomplicate this and use things like semantic monitoring. I would also say getting really kind of formal about versioning and that's version numbers isn't super important in some situations, right? Within a team, when you've got 2 microservices that talk to each other, just don't worry about it. You can talk to each other, you can work it out between you. If you're exposing an API, though, to the public, to the outside world, you're going to have to be super formal and super careful about those changes. But I wouldn't be revving versions just because I've added a piece of functionality which is still backwards compatible. Adding a new optional field shouldn't require a brand new version number in most situations, I think.
Thank you, Sam. Before we move on to some other questions, just some compliments from everyone. Bjorn is saying, really great talk. Thanks. Danny saying, great talk, very inspirational. I completely agree about the fact about going completely from one side to the other. Russell is saying, Sam is awesome. Thoughtfully recommended his advice. So yeah, great feedback you have here. And a few more questions we have, and we are going to answer all of these. We have time to do that. So another question: do your microservices always return to Do your microservices always return a DTO, even if a domain model is exactly the same as that DTO? Do you separate a model from DTO only when you change when the change happens?
So I wouldn't automatically always put in a DTO. What a DTO does is it allows you separation of your internal representations and your external representations. So if you feel the need to separate those 2 worlds, a DTO can be useful. There is a challenge and a danger to just automatically saying that my domain objects get exposed over an outside interface. Remember, domain-driven design doesn't say that. Right. So if we think about a microservice modeling of bounded contexts, a bounded context in domain-driven design is explicitly about the idea that some domain concepts are hidden inside the boundary and some domain concepts are exposed over them. But the bounded context in domain-driven design is about being explicit about those things. If you're adopting the kind of idea of bounded context and you're using domain-driven design to drive your microservices, it follows, therefore, that you should expect to have some domain objects which are never exposed outside your domain boundary and some domain concepts which are. A DTO, if it helps you particular have a separation between those things, can be useful. Now, if I had created an object that represents a domain object that I want to share over a boundary, and initially it's a direct mapping, I'm not going to worry about putting a DTO in. However, I would want to put something in that catches me if I make a mistake that's going to break compatibility. When I then maybe make a change, like in the example I gave, I went from having the field called an age to calling the field a local date. I could at that point change that, then bring in a DTO. So it could easily be something you add in later on. I think I wouldn't necessarily automatically put a DTO in. The other thing I would say here is that there is a danger as well that we fall into inside out thinking. We think because this is a domain object that I've got, I'm going to expose it. And that's thinking inside out. Even worse can be, well, that's what's in my database. I'll stick that on an API, right? I see a lot of GraphQL frameworks that do this right now, and it drives me mad. That's the wrong way to think about it. You want to think about your microservice from the point of view of the consumer. Speak to your consumer. What is it that they expect? They actually might want that same information in a different structure. So just automatically giving people what you think they want doesn't make sense any more than just giving a user interface to a customer without thinking about what they want makes sense. So you've got to ask them what they want, think about the design of your API outside in, and a lot of the time that will tell you the things that you don't need to expose. And then that might also push you towards something like a DTO. So not required, but can be useful.